Yeah, always a privilege to introduce John. John worked for many years at JPL before coming to NASA headquarters, and then I believe you were there, weren't you, about 14 years, 15 years, yeah. And some few years ago, he formed his own company and works out of Central California now. Artemis is the name of your company, and you have another one too, don't you?
Yep, it's just one of them. Thank you, John. Good afternoon. I was thinking at first that it was probably a bad thing to go after John Rather. Now I am convinced.
Dean, due to his overrun, you've got 7 minutes.
Yeah, exactly. Yeah, 70 minutes should be about fine. I'm a little hard of hearing. Anyway, I did restructure my talk a little bit to conform slightly better with the general outline of this portion of the symposium. What I'd like to share with you is both an idea for how to pursue space solar power as well as basically a decadal plan for how to make it happen. So I assume everyone here is familiar with the vision. It's a very attractive idea, originating in the 1960s. This, as it happens, is the 50th anniversary. This year is the 50th anniversary, and this month we're now about 2 weeks ahead of the 50th anniversary of the publication of Peter Glazier's seminal paper in the journal Science, articulating for the first time the practical invention of the solar power satellite. There's quite a rich history there, which is not my topic this afternoon. But essentially, space solar power is the idea that if you could harvest solar energy in space nearby the Earth and deliver it economically and efficiently to and safely to markets on Earth, that you have the opportunity to significantly increase the use of solar energy to power modern civilization. The rationale really lies in the fact that the sun doesn't shine that well in many of the places where people like to live. The sun shines exceptionally well in Arizona. A remarkable number of people choose to live in Germany and Japan and Canada and the Philippines and places where the sun does not always shine. And you can have overcast and, in fact, bad weather for weeks at a time. This makes the very wide-scale application of solar energy for base load power highly problematic. And that's why space solar power has been so interesting. Unfortunately, the concepts that were articulated in the 1960s, and again in more detail in the 1970s, followed traditional spacecraft systems architectures. They're essentially the idea that a spacecraft is very much like an aircraft. It's a single monolithic system. It's typically fabricated in a laboratory environment. It's a clean room. People wear booties and gloves to avoid electrostatic shock to the electronics. And these things require an investment on the order of tens of thousands to hundreds of thousands of dollars per kilogram to manufacture them. They involve integrated power management and distribution with integrated sources of power, typically solar arrays, integrated thermal loops to get rid of the waste heat that is generated by the inefficiencies in their electronics inside the box of the spacecraft, and integrated wiring harnesses to allow the piece parts of the spacecraft to communicate. This is all hand integrated, a great deal of touch labor, and is the reason why all of these systems, even the GPS, which was manufactured in somewhat larger numbers, have exceptionally large costs per kilogram for the hardware. It's often been said that it is the cost of launch that is the most terrible for a solar power satellite, and I have always disagreed with that assessment. if you start with the conventional satellite and you try to build one that is the size of a solar power satellite, it's a stupendously large object, it would cost an extraordinary amount of money per kilogram of hardware. The cost of launch, even at, say, $20,000 a kilogram, which is consistent with conventional expendable launch vehicles, is a fraction of the hundreds of thousands of dollars per kilogram that a conventionally designed and implemented solar power satellite would cost. So I approached the problem when I first got involved in this, and then over the last 25 years, from the standpoint of first reduce the cost of the hardware before, and then other things will come. The other necessaries will come. And the approach that I used, which is another way of articulating the vision of von Neumann machines, which John described a few moments ago, I describe as the hypermodular architectural approach. This we see constantly in nature. Bees and ants and even multi-species hypermodular systems such as coral reefs, in which you have multiple organisms at various scales cooperating to achieve broad functional functions of value to that organism. And so my proposition was that if we did large-scale space systems using the metaphor of an adaptive and robust system of systems involving multiple organisms, multiple entities, multiple species, as our guide, this is the way to achieve very large systems in a robust and affordable fashion. Hence, my concept for the solar power satellite, which I describe as SPS Alpha, which is solar power satellite by means of arbitrarily large phased array. The idea is that you have a very large number of CubeSat-sized, 2U CubeSat form factor, so about that size, 10 centimeters by 10 centimeters by 20 centimeters is the nominal, in very large numbers, connected by simple deployable or in-space manufactured structures such as those that Rob Hoyt was describing, where all the power generation and the thermal management is local, and all of the communication among the modular elements is wireless. So you get rid of the thermal harness, you get rid of the data harness, you get rid of the power harness, you distribute energy on board the platform in the same way that energy is distributed by one of these large solar thermal power plants in the deserts. I think you may have seen one at Ivanpah. We have a very large number of reflector elements that individually point towards their target. Well, in this case, you have a very large number of thin film optical systems. So this is a large optical system of the sort that John was describing, which redirects the sunlight down to an array of PV modules which are locally connected at low voltage to an array of wireless power transmission modules. This particular one is an RF module. I will mention for Phil's benefit, there's no necessity that it be an RF module. It could easily be a laser module. That the architecture doesn't care what's on the front end. The front end is just the business end of the system. The point is to take incoming sunlight, to redirect it without a massive high voltage power management and distribution system, and without the associated thermal management, to power conversion connected by structures and by a very large number of these small intelligent modular systems to the working front end. The key performance parameters, and this is not to get into the technical details because that's a much longer conversation, key performance parameters in the current version of SPS Alpha are about 5 kilograms per kilowatt delivered to the market using wireless power transmission at the 2 gigawatt level, about $100 per kilogram hardware cost, and approximately 1 million modules for the 2 gigawatt class system. How does this turn out? Well, the key assumptions, obviously all the key factors come down to hardware cost, launch cost, and the allocation of spectrum, which is a policy issue, but it's so critical that it can't be neglected. It has to be at least be mentioned. And this takes information from the Energy Information Agency's forecast, both the current data and forecast of the price per kilowatt hour, the levelized cost of electricity that can be delivered by a wide variety of energy sources. And because the cost per kilogram with this hypermodular approach, this large number of small, independently but mechanically connected modular elements is so low, it means that even with costs of about $5,400 a kilogram, i.e. consistent with the Falcon 9 price point that they list online, you can get cost of electricity of approximately 12 to 15 cents a kilowatt hour. Now that's not great shakes in West Virginia, but it's a really good price for Germany. It's a very good price for Japan. It's a very good price for the Bahamas, where they basically generate their power by pressurized natural gas or liquefied natural gas that's shipped in large tankers. So this is already competitive with a number of markets. And if you can reduce the cost of launch down to about $600 a kilogram, not $200 a kilogram, but only at about $600 a kilogram, you have the opportunity to get prices, the levelized cost of electricity, on the order of 3 to 4 cents per kilowatt hour. And to do that without any magic in terms of radically advanced conversion efficiencies or really super lightweight structural elements, my 5 kilograms per 5 kilograms per kilowatt is all worked out in great detail, not to go into it here, but the numbers are not overly optimistic. One of the reasons why this is an especially interesting idea for the purposes of a decadal plan is that, unlike the solar power satellite, as originally envisioned by Peter Glaser, which was this very, very large thing, 10,000 volts, bare wire, kilometers in size, a single system, all of those things. Because this comprises a very large number of modular pieces which operate largely independently, except for being mechanically connected, there are a great many other markets where such modular platforms and systems can have utility, both in the communication satellite market, in the application to large platforms such as radiometers or radars looking toward the Earth, as well as power for in-space applications such as lunar surface operations or lunar operations, and power for surfaces. In another paper, I looked in some detail at the power requirements for a truly self-sufficient human habitat, i.e. for space settlement. And this takes into account not all the other the details of the water processing and so on, but rather using Indiana as my baseline. Indiana is a pretty good baseline. It takes about 4,000 square meters per person to support people based on a place like Indiana. A place like Arizona, it's more like 10,000 square meters. So this is a pretty fertile but not super. It's just a good farming state. So I take that as my baseline. There's no super hydroponics. There's none of that stuff, because most of those things depend on feedstock that comes off the platform, off the page. You just don't worry about where you get all those fertilizer salts and so on. Well, Indiana is largely self-contained, and it works out to be about 500 watts per square meter steady. And if you take into account the amount of power per square meter and the number of square meters, taking these assumptions, you end up to have a truly self-sufficient space settlement of 120 people, where you could basically grow a ham sandwich, which is, it's a really critical litmus test. It works out to be about 300 megawatts of power constantly. So the other, traditional life support systems are this includes all the water processing, all the purification, all the air, everything that went into making Indiana. And it's about 300 megawatts. Now, these numbers may be wrong, but they're not wildly wrong, and they are based on a really clean set of assumptions. Now, then the question becomes, if humanity is going to move across the solar system, how do we do it, given that we now know we need about 300 megawatts per 120 people? And the answer is with SPS alpha, because this architecture has as its virtue that in going from one place in the habitable zone to another, or going beyond the habitable zone around our star, the only thing you really have to change is the size of the concentrator. And this just shows a set of curves, and I because I knew time was short this afternoon, I'll just show this to you. As you, of course, move away from the sun, what you find is that the illumination diminishes, the insolation diminishes. At Earth, it's about 1,370 watts per square meter. At Mars, it's about 590 watts per square meter, and so on. And so as you move away from the sun, or you end up with less and less sunlight, and a requirement for more and more concentration. I've actually looked at a series of specific cases, such as Ceres, Mars orbit, Enceladus, i.e. locations beyond, I only went as far as Jupiter. You get beyond Jupiter, it gets kind of silly. And the places where you can put a solar power satellite change based on the location, i.e. Earth, it's about 35,000 kilometers to geo. Mars, it's about 17,000 kilometers to aerosynchronous Mars orbit, and so on. That's this second curve here. This looks at the places where you might put a solar power satellite to deliver power to your 120-person permanent biosphere. It's really sorry the biosphere guy did not show up, because I was all ready for this. And you end up with an increasingly large reflector. But as it happens, the reflector and its structure, the structure is essentially the small smart interconnects, plus a lot of structure just like the gentleman from Hoyt Tether. Is he still here? No, he's not here at the moment. Anyway, structures just, oh, there you are. Sorry, you were out of my field of view. Anyway, just like you were talking about, you can make those wherever you go. So you have to deliver a certain amount of fixed mass, i.e. the smart phased array, and the brilliance of the little interconnects, not their structure, not their housings. Those things can all be 3D printed. But you end up with a fixed total mass that you have to bring, and then a variable mass which is increasing as you go away from the sun, but is all locally producible, i.e. an increasingly large concentrator. And you maintain the same level of concentration on the PV cells, same temperature, and so on. So this is a way for a single common architecture which can be pursued with using in the lab technology to enable humanity to actually think about living in diverse locations around our solar system. So the decadal plan to realize this. In about 12 months, with a couple of $1 million, it would be entirely plausible to fabricate, integrate, and test not only the robotics, but also these modular interconnects and their structural elements, because so much work has been done in the relevant fields. How many people, how many companies, how many universities make CubeSats? All my interconnects are a very different morphology with different plugins. It's sort of like a Lego version of CubeSats. And so it's a couple of $1 million in about 12 months. Then to build the flight model, but not to go to flight, but the engineering model for all the flight-like versions, and get the robotic assembly done and tested in low Earth orbit, assuming somebody else pays for the launch, this does not include the launch, is about $15 million. And then to go to a low Earth orbit demonstration at about 30 kilowatts worth of these modules, now assembled into a demonstration satellite, is about 150 million, including the launch. And so for about a couple of $100 million, give or take, and 4 years, you can get all of this to flight demonstration. And then it really is only a question of improving the technology of the components. For example, everybody knows it's a lot rougher radiation environment in GEO than it is in LEO. So you'd have to take all of the electronics that you had originally built into the LEO demo and upgrade them for operation beyond the Van Allen belts and so on. But it's on the order of a decade, depending on the size of the platform, because what you're talking about at this point is simply how many of the modules do you want to buy, and then how many do you want to assemble. And this goes directly with the cost of the system and the project. But it's about 10 years, a decade, to get to the point of large-scale, 100-megawatt class SPS platforms that would allow humanity to operate anywhere the sun shines. Now, beyond the first 10 years, what about introducing lunar materials, since the moon is a critical part of U.S. policy at the moment? And the answer is, it's maglev on the moon. A very good friend, Bill Escher, who's no longer with us, invented back in the 60s, shortly after Danby and Powell invented maglev. Bill Escher came up with the idea of employing maglev for lunar launch. And of course, it doesn't have to be high acceleration. This is not a coil gun, rather about a gigawatt, and the solar arrays can be deployed along the path of the maglev system for about 3 Gs, 4 Gs. You can launch hundreds to thousands of 20-ton payloads from the moon every day at max, all solar powered. And the recurring cost is on the order of $25 a kilogram, and that would reduce the cost of the solar power satellite that I mentioned previously to less than a penny a kilowatt hour, because you're at the point where it's all the cost of the launch. And of course, you're still bringing from Earth all the brilliant stuff, all the chips and so on, but the structural materials, the boxes into which everything gets integrated, all of those things would be coming from the moon. So in conclusion, space solar power done in a hypermodular way using in-space printable von Neumann-like machines, which are assembled to make the very large system, can be realized on order of a decade. Doing that way and relying on the independent development now of a variety of launchers, which can both launch large payloads and/or launch them at very low cost, allowed the option for early space solar power applications, particularly for space exploration and development at affordable prices. And within 10 to 15 years, these systems could be operational with clear, tangible milestones, i.e. making things that are on the order of kilograms and then making scores of them and then making hundreds of them, putting them together and demonstrating them in space. All could be done quite credibly within the next decade. Thank you.